Bismillahirrahmanirrahim. Assalamu alaikum, dear student. My name is Dr. Muhammad Adnan Sagar, and today the topic of our discussion is synthesis and design of inorganic materials under the subject of advanced inorganic material chemistry. Dear students, so far we have discussed some of the important aspects of the said title, and we have discussed very important synthetic techniques for the designing and for the synthesis of recent inorganic materials that have multiple applications in all walks of field. Dear student, in the last lecture we have discussed about the intercalation and deintercalation, in which we have studied if some of the small molecules, ions or atoms, if resided in the spaces or interstices present between the atoms of a molecule, then what would be the different benefits and applications of these intercalated and then deintercalated compounds, and what are the specific methods and what are the easy routes for the synthesis of these kind of desired materials. We have discussed a lot about this intercalation and deintercalation processes and compounds. Moreover, graphite intercalated compounds uh, studied a lot under the subject intercalation and deintercalations. And today, the major topic of our discussion is pillared clays and layered double hydroxides. Many other layered structures undergo intercalation. Other intercalations, many other structures may undergo intercalation reactions to form new materials, often with interesting and novel properties. Such reactions have been known for many years in clay mineralogy. Clays such as kyanite, which was Al2OH4 Si2O5, have layered silicate structures in which the layers are either electronically neutral, as in kaolinite, or charged, as in mesocovite, which is actually potassium Al2OH4 2 AlSi3O10, in which the layers have a net negative charge per formula unit due to replacement of one Si4 plus by Al3 plus. In this, muscovite already contains interlayers of potassium ions to give the structure some three-dimensional rigidity, whereas in kaolinite layers are usually held together by hydrogen bonding, giving a mineral which is much softer, as we have discussed in talcum powder. So in muscovite, actually potassium ions are somehow very important to establish the three-dimensional structure of this compound. Various ionic and molecular species can intercalate between sheets of clay mineral structures. In pillared clays, the potassium ions of muscovite can be ion exchanged for large complex aluminium cations such as Al13O4 OH24 H2O12 7 plus, and because of their size have the effect of pushing apart the silicate sheets. On heating the product material, the aluminium complex cation dehydrates and residue forms strong covalent bonds with silicate sheets. It will produce a pillared structure with a porous two-dimensional interconnected network. However, layered materials that behave similarly to clay materials are layered double hydroxides, which is commonly known as LDHS, and zirconium phosphonates. LDHS, which is the layered double hydroxide compounds, have positively charged metal hydroxide layers of journal formula, which is M2 plus 1 minus X, M3 plus X, OH twice X plus, while the metal 2 plus may be the magnesium or nickel, etc. While in the case of if a metal is 3 plus, then it should be aluminium 3 plus, iron 3 plus, etc. And X is in the range of zero point 0.2 to 0.33 for single phase solid solutions. In these compounds, similar sized M2 plus and M3 plus cations are highly disordered over the octahedral sides in the layers of edge sharing octahedra, which is actually showing in this diagram. These layer double hydroxides LDHs are actually contain a mixture of water molecules and anions, such as the anions may be the carbonates, nitrate, halides, iron cyanides, and oxalate, that is actually establish a link between the sheets. Layered double hydroxides LDHs find applications as ion exchangers and may be used as a catalyst and sorbents. Moreover, they are increasingly are of interest for the intercalation and release of organic and biologically active molecules. Clay minerals are well known for their ability to intercalate organic molecules, and layered double hydroxides behave similarly under appropriate conditions. These examples are actually shown in this diagram. This is actually schematic diagram of the interaction of either organic molecules which can be subsequently polymerized in situ, or for the direct intercalation of either organic molecules which can be subsequently polymerized in situ, or indirect intercalation of some polymer molecules. Clay minerals and LDHS with low charge density on the octahedral sheets are readily able to exfoliate and separate the sheets, especially if they are only held together by weak hydrogen bonds. Then it is quite easy to exfoliate and separate from the sheets. If they are held together by weak hydrogen bonds and subsequently restack the sheets, With LDHS, this process is not so easy given the charged nature of the layers, but is possible in certain cases as shown in this diagram. Recent research shows that it is possible to intercalate a range of biologically active molecules such as vitamins, amino acids, and in future LDHS may find the applications in medicine as drug and gene delivery systems. LDH materials can also take part in anion exchange reactions with polyoxometalate anions such as PW12O43 minus to form pillared products. In some cases, it is not possible to introduce large anions in a single step, but a two-stage reaction introducing anions of increasing size which gradually push apart the layers of the host structure. After showing the synthesis of polymer intercalated LDH, now we would like to talk about the synthesis of graphene. Graphene is actually a single sheet of carbon atoms that form hexagonal rings as in graphite. It is shown in this diagram. It had been thought that a single flat graphene layer would be intrinsically unstable until the amazing simple discovery by some scientist at Manchester University. And subsequently, they were awarded the Nobel Prize in Physics in 2009 that individual graphene layers could be peeled off a graphite block using scotch tape. This method and subsequent discovery of several unusual physical properties exhibits by graphene is the latest stage in a remarkable series of fundamental advances in the chemistry as well as in physics of carbon, and it is shown by the following timelines. As we can see, in 1954, the synthesis of artificial diamonds by HPHT, while in 1981, synthesis of diamond films by low pressure gas phase deposition. Onward 1985, the discovery of buckyballs, which is actually one of the allotropic form of carbon, in which C60 will be the basic unit, discovered in 1985. In 1992, the synthesis of carbon nanotubes, while in 2004, synthesis and subsequently the characterization of graphene was done. This rich variety of carbon structures actually arises for two reasons. First one is because of the ability of carbon to exhibit three hybridized bonding states, that is sp hybridized carbon characterized by linear coordination and including one triple bond, sp2 hybridization characterized by triangular coordination and one double bond, and sp3 hybridization with tetrahedral coordination and one single bonds to four neighbors. And the second one was because of the ease of catenation, in which carbon atoms form bonds to other carbon atoms and subsequently leading to a large variety of two-dimensional and three-dimensional structures with a carbon backbone. These two unique properties of carbon actually depicts that carbon have variety of can show variety of properties by using catenation and sometime the different hybridized state of carbon atom with other carbon atoms. For example, we can see the diagram of graphene, in which we can observe that carbon atoms are just arrange themselves in such a way that they can form a huge layer. It's a kind of two-dimensional layered structure, and that would be quite helpful for different applications in recent chemistry materials. In recent research, graphene exhibits a quite interesting properties in water filtration systems. It have a great permeability properties that actually exhibits a very nice results to give to for the purification of water. Graphene was first synthesized by a simple mechanical route of peeling layers from the piece of graphite. The graphite which were then actually transferred to a silicon substrate. High quality graphene layers can be obtained in this way and have been much used for property measurements. Since then, numerous chemical routes have been devised for exfoliating or separating graphene sheets, because graphene sheets actually intercalate with each other and form uh, multiple sheets from graphite. So this is quite interesting to learn numerous chemical routes which would be helpful for the exfoliating or separating of graphene sheets from the bulk multiple sheets. This is an ongoing topic of research to establish routes for preparing high quality graphenes which are free from impurities and which are either single layer graphene or graphenes with a controlled number of layers. And this is very important to get a single sheet of graphene which would be the two-dimensional in nature. And if we want to observe some experiments on graphene, then it is quite important to have a controlled two-dimensional structure and sheet of graphene, or we have a specific layers of graphene sheets for the successful study of the experiments. One method is to first prepare single layer graphene oxide, which is commonly known as GO in international market. This first method to prepare single layer graphene oxide by a sequential chemical treatment of graphite powder with concentrated sulfuric acid, sodium nitrate, potassium permanganate, and H2O2. It is actually followed by ultrasonification to separate individual layers of graphene oxide and from the colloidal suspension in water. The synthesis of graphene oxide single layers by a sequential chemical treatment of graphite powder with sulfuric acid, sodium nitrate, KMnO4 and H2O2, which is followed by ultrasonication to separate individual layers of graphene oxide and form a colloidal suspension in water. The suspension is then reduced with hydrazine hydrate, and most or all of the oxygen should be removed. Other reducing agents can also be used. By varying the conditions, single layer or multi-layer graphene may be obtained. Other methods include salvothermal treatment with sodium in ethanol, ultrasonication of graphene oxide in surfactant water solution, or N-methylpropylidene microwave assisted exfoliation and reduction of graphene oxide with hydrazine hydrate. Numerous gas phase routes to graphene have also been devised. These include actually the thermal exfoliation of graphene oxide by briefly heating at about 1050 degrees Celsius in the presence of argon. It also includes the heating nanodiamond in an inert atmosphere. The inert atmosphere may be provided with the help of nitrogen gas or liquid nitrogen. It will actually flush out the oxygen in the atmosphere or in the premises of reaction. It also includes arc evaporation of graphite in the presence of hydrogen. It includes epitaxial thermal decomposition of silicon carbide, in which the outer layer of an oriented single crystal of silicon carbide in the 001 orientation is heated, which is actually for which is actually to remove the outer layer of silicon and leave a graphene surface layer. Chemical vapor deposition, which is CVD, of the various hydrocarbons on metal substrates. The metals may be nickel and copper. So these are the some important aspects of graphene and the different synthesis route of graphenes with possible applications in the chemistry as well as in physics. The important one was the actually hydrothermal and salvothermal treatment with sodium in ethanol, while ultrasonication of graphene oxide in surfactant water solution, or N-methylpyrrolidine microwave assisted exfoliation and reduction of graphene oxide with hydrazine hydrate. These are the different parameters and different routes for the uh, synthesis of graphene. This is all about this lecture, and thank you very much.